In 2021, a mid-sized gaming company launched a new title that immediately went viral. Within 30 minutes of the announcement, traffic was 40 times the expected baseline. Their auto-scaling configuration was solid. They had prepared for a spike, and the application servers responded exactly as designed, multiplying from 8 instances to 94 in under 10 minutes. The metrics dashboard looked like a success story. And then the application fell over completely. Not because the scaling failed, because the database behind those 94 servers had a hard limit of 100 simultaneous connections, and 94 application servers, each maintaining several database connections, had just exhausted it. New requests arrived at the application tier, got handed to a server, and that server reached for a database connection that did not exist. Errors cascaded. The site went down. The auto-scaling had performed flawlessly. The system had still failed. This is the limit that most explanations of scaling never reach, because they stop at the application tier and treat it as though it exists in isolation. It does not. Every application is a chain of components: servers, databases, caches, third-party services, internal APIs, and a chain scales only as far as its least scalable link. Imagine a motorway that has been widened to handle a surge in traffic. Originally 2 lanes, it has been expanded to 8. Cars flow freely, merging and accelerating, the journey smooth in a way it never was before. Then they reach the toll plaza at the far end of the motorway. The toll plaza has 2 booths. It always had 2 booths. Nobody widened the toll plaza. All 8 lanes of traffic are now funneling into 2 payment points, and the queue stretches back kilometers. The motorway widening worked. The engineers who designed and executed it did their jobs perfectly. The commuters are still sitting in traffic for an hour. The bottleneck did not disappear. It moved, and in moving it became more visible, because now the entire pressure of 8 lanes is concentrated at 2 points rather than being distributed across 2 lanes. This is what happens when an application tier scales, while its downstream components do not. The extra capacity you added does not dissolve the bottleneck. It intensifies it, because more servers means more simultaneous requests reaching the component that cannot keep up. There are 3 distinct categories of limits worth understanding, because each one requires a different approach to find and a different approach to address. The first category is provider quota ceilings. Cloud providers are not infinitely elastic in practice, even though elasticity is their promise. Every provider imposes service quotas, limits on how many of a given resource a single account can consume in a region. There may be a limit on how many virtual machine instances you can run simultaneously, a limit on how many concurrent function executions a serverless platform will allow, a limit on how many IP addresses can be assigned to your network, or how many load balancer rules you can configure. These limits exist for legitimate reasons. They prevent a single customer's runaway scaling event from consuming resources that other customers depend on, and they give providers some control over capacity allocation across their infrastructure. The critical thing about quota ceilings is that they are invisible until you hit them. They do not produce a warning at 70%. They do not slow you down gradually as you approach them. They produce a hard stop. Your scaling policy requests another batch of servers, and the provider returns an error, limit exceeded. The auto-scaling infrastructure then behaves exactly as if it had successfully provisioned new capacity. It records the action, moves on, while in reality, the new servers never appeared. Traffic continues growing. Existing servers continue to saturate. From the outside, it looks exactly like a scaling failure of unknown origin, until someone checks the provider's quota dashboard and finds the ceiling. The fix for quota ceilings is to find them before your traffic does. Most providers make quota limits visible in their console, and most will increase limits on request if you can justify the need. Engineering teams preparing for a known traffic event, a product launch, a marketing push, a scheduled broadcast, should audit their quotas in advance and request increases with enough lead time for the provider to approve them. This is operational hygiene that most teams only discover they needed after the first outage. The second category is downstream component bottlenecks. This is where the toll plaza lives. Your application servers scale horizontally. That is the whole point of cloud infrastructure. But the components they depend on may not share that property. Relational databases are the most common example, and the one that catches teams by surprise most often. A relational database manages connections as a finite resource. Each connection consumes memory on the database server. When you have 8 application servers, each maintaining a small pool of database connections, the total number of active connections is manageable. When autoscaling expands that fleet to 80 servers, the total connection count grows with it, and the database, which has not scaled, runs out of connections to give. Queries begin queuing. Response times stretch. Eventually, the database stops accepting new connections entirely, and every request that requires a database query fails. Third-party APIs present the same structure in a different form. If your application integrates with a payment processor, a mapping service, an email delivery platform, or any external API, that service has its own rate limits, a ceiling on how many requests per second or per minute it will accept from your account. Scaling your fleet from 10 servers to 100 does not scale your API allowance with it. 100 servers collectively hitting an API rate limit produces the same errors as 10 servers hitting it, just faster and at larger volume. You have scaled your ability to make requests faster than your permission to make them. Caches, message queues, logging aggregators, internal authentication services. Any shared component that many instances of your application depend on simultaneously can become a bottleneck as the fleet grows. The application tier scales. The shared component does not. The bottleneck moves to wherever scaling stopped. The third category is infrastructure drift, and it is the subtlest of the three. Systems are designed and tuned at a particular scale. Thread pool sizes, connection limits, timeout configurations, log rotation schedules, monitoring sample rates, all of these are set with a particular fleet size in mind. When the fleet doubles or triples under sustained load, these configurations do not automatically adjust. A logging agent configured to ship logs from a single server without issue can overwhelm a centralized log aggregator when 100 copies of it are all shipping simultaneously. A monitoring system configured to collect metrics from 20 servers may begin dropping data when asked to handle 200. An internal authentication service designed to handle a modest request rate becomes a bottleneck when the application fleet has grown 20-fold and every new request requires a token validation. Infrastructure drift is hard to find because it is distributed across many components, each of which was correctly configured for the scale it was designed for. No single component failed through negligence. What failed was the assumption that configurations valid at one scale remain valid at another, and that assumption is almost never explicitly tested. The pattern across all three categories is the same. Scaling the component you can see does not automatically scale the components you cannot, or the ones you are not watching, or the ones you assumed would handle more without ever verifying that assumption. The application tier is the most visible part of the system. It is rarely the only part that matters. Finding your limits before demand does require deliberate effort. Load testing that goes beyond the application tier and stresses the full chain of components. Quota audits that surface ceiling numbers before they become incident numbers. And architectural review of which shared components are load-bearing for a scaled fleet in a way they were not at baseline. What you understand now is that scaling has a boundary condition that is not set by your auto-scaling policy and is not visible in your server count metrics. It is set by the least scalable component in your system, the toll plaza at the end of the motorway, unchanged while everything around it expanded. Finding that component before your traffic does is one of the most valuable things you can do with the time before a spike arrives, because once the spike is in progress, the wall you never looked for is the one you run into first.